Now that we've seen the basics of how filters are working, we can go about constructing one and simulating its response. So first we're going to look at making what we'll call a passive low pass or LP filter. So it is passive in that it won't involve op amps, it won't involve any external power. We won't get to that in this course, but I'll talk about that a little bit at the end. And it's a low pass filter, meaning that we are going to select some cutoff frequency, and in general, frequencies below that are going to be preserved, and signals with frequencies above the cutoff are going to be attenuated or removed from our signal. So the general form for a transfer function for a first order low pass filter is going to be in this form that we see this g of s. So again, we have our s term in the denominator. We have a 1, so it's in the standard form that we've seen previously when we were looking at the response of a first order system. And now it's written a little bit differently here. You see, instead of this tau times s plus 1, it's written as s over omega c plus 1. So a couple lectures ago when we talked about first order systems, I talked about how tau, the time constant, is when we give it a step input, it's going to tell us how long it takes to get to about 63% of the steady state response. But here, where we're going to be giving it this harmonic input, or we're going to see the sum of harmonic inputs, the tau, or really 1 over tau, is going to be the cutoff frequency. So in this example, we are going to design a filter with a 5 Hertz cutoff, a low pass filter with a 5 Hertz cutoff. And we're going to see what happens when the input into our transfer function, specifically this filter, is this harmonic signal made up of 2 harmonic signals. We see it's 5 sine 0.5t plus 0.6 sine 100t. So the input that's going into our filter has these 2 parts, a lower frequency but higher amplitude part, that's the 5 sine of 0.5t, so 0.5 radians per second. And then we're adding to it a high frequency signal that has a lower amplitude, the 0.6 sine 100t. So this is different than some of the examples we've seen before because we have 2 harmonic signals, 2 sine waves that are being added together going into our filter. But our analysis is going to behave pretty much the same. We're going to term by term see how is this signal affected by the Bode diagram. And again, by this design with a low pass filter, what we should expect to happen is that the signals below 5 Hertz are going to be more or less preserved, while the signal parts that are above 5 Hertz should be attenuated. So in this case, with this 2-part input, we should see that the high frequency 100 radians per second should be gotten rid of through the filter while we preserve the 0.5 radian per second signal. And we'll show this also in simulation. And then we're going to look at how can we make this in hardware? How can we make an analog filter that would do just this? So if we want this 5 Hertz cutoff, we have to set omega c to 5 Hertz. But really we need to set it to, we need it in radians per second, so we're going to multiply it by 2 pi. So we're going to make this omega c equal to 2 pi. And then that's going to be the transfer function of our filter. So moving into MATLAB to do our design, to see our Bode diagram, and then to see in simulation how it's going to behave. So we see here, 254, I'm deciding what my cutoff frequency is. So yeah, it's 5 Hertz, but I need this in radians per second. So I multiply it by 2 pi, and I get 10 pi. In 257, I'm going to make my filter, or the transfer function for my filter. So just like we saw in the slide, the general form is going to be this 1 over s over omega c plus 1. And then we're going to see the Bode diagram of that. So let me just run it so far here. If we look at RF1, we see that we get exactly what we had on the slide, but specifically for a 5 Hertz or 10 radian per second cutoff. And now I want to make the Bode diagram of this. And we can see what its response is going to look like at these multiple frequencies. So again, the idea here is that our input is made up of 2 frequencies, a 0.5 radians per second and a 100 radians per second. But first we can look at a couple things about this Bode diagram, again specifically talking about filters. So one, we have the cutoff frequency. The cutoff frequency is really defined as the point where our magnitude is going to be equal to root 2 over 2. That's in the linear form. So we can translate that into decibels. So I'll do that here. So 20 times log 10 of the square root of 2 over 2. That's going to translate to about -3 decibels. So we want to see where is our magnitude equal to -3 decibels. Well, really it should be at, or will be at, the cutoff frequency. So let's double check that in our figure here. Right, so on the Bode diagram, let's see where this happens. So it looks around here. Move the magnitude over a little bit. We get, this is close enough, a magnitude of -3 decibels, about, with rounding, happens at 31.4 radians per second. So again, here we're at 5 hertz times 2 pi to put it into radians per second, 31.4. Again, back to our figure, 31.4, so it does match. So once again, the cutoff frequency is at -3 decibels, or a linear value of root 2 over 2. So that is confirmed that we made the transfer function correctly. Now when we look at the Bode diagram for this transfer function, again, we've identified the cutoff frequency, but notice in this first order filter, what's happening here. Ideally, the cutoff frequency is going to be the marking point between the frequencies we want to keep and those we want to get rid of. So in an ideal filter, what we would love to see is that the magnitude is really flat at 0 decibels and then makes a very sharp decline, pretty much a vertical line, and then has a very, very low decibels for everything above our cutoff frequency. That'd be an ideal filter. This real first order filter, passive filter, doesn't do that. So notice that we have, again, this is where we see this roll-off concept, that the magnitude is going to start declining. It gets to -3 decibels at the cutoff frequency, and then it continues to decline. So any frequencies we would have in this mid-range here are going to be a little bit attenuated, but not too much. And that's going to keep getting more and more attenuated at those higher frequencies. So something we just want to be aware of is, one, just because we're below the cutoff frequency doesn't mean there's going to be no attenuation. We see that we can have up to -3 decibels of attenuation, and maybe those are some of the signals we want to keep. And just directly after the cutoff frequency, we're not completely getting rid of any signal that is at those frequencies. It's going to take a little bit of time before we can really tamp down on those things that are happening above the cutoff frequency. But once we're sufficiently above the cutoff frequency, yes, those are going to have a very low magnitude. They're basically going to go away. And if we are sufficiently below the cutoff frequency, all of that signal is going to be more or less preserved. So we see here it basically drops to 0 by the time we're at about 6.5 radians per second. Those are going to be all preserved. And last thing on this, we want to be looking at the phase diagram. Again, it's going to start to become off of 0 as we get near that cutoff frequency. And we keep traveling, and now the phase is going to get smaller and smaller and smaller as it gets asymptotically towards -90 degrees. So again, signal that we want to keep, the stuff that's below the cutoff frequency, we are introducing at those frequencies this small amount of lag that we want to be aware of, that we're going to have a little bit of a time delay in once we go from the input of our filter to the output of our filter. So we want to be careful in our selection of the cutoff frequency and be cognizant of the Bode diagram that signal at frequencies we think we want to keep are going to be far enough below the cutoff frequency that we're not introducing too much lag or reducing their magnitude too much. But on the other hand, we want the cutoff frequency to be low enough that we are going to be tamping down and really making a very small magnitude on the frequencies that we want to get rid of. Now what we want to look at is how is it going to affect the two parts of our input signal. So quickly going back here, the sine 0.5t, so we're going to have a 0.5 radian per second signal, and also the 100. Right, so if we go down here to 0.5, our frequency of 0.5 radians per second, there we go. And then 100 is going to be over here. Okay, so what we see happening are, at least on the magnitude diagram, two different things happening. We see for the low frequency that the magnitude is going to be pretty close to 0. Let's just call it 0 for this, which means that really no change. The signal comes in at amplitude of, here we see 5. It's going to leave about 5. It's going to be a little bit lower, but more or less it's going to be 5. But we're going to see something different happening. For the 100 radian per second signal, we have a magnitude here of negative 10.5 decibels. So that means that this signal is going to be attenuated. So again, if we convert this now back into linear, if I say 10 raised to the negative 10.5 over 20, we should see it comes to about 0.3. So the high frequency signal is going to be cut down to about 30% of its original amplitude. And that's what makes this a low pass filter. The low frequency will be more or less 100% of its original amplitude, whereas the high frequency is now going to be 30% on the other end. All right, so that's on the analysis side, looking at the Bode diagram, how it should behave. Let's see in simulation how it actually does. So I'll make this second figure here. So I'll have 15 seconds of this input. That's what I'm doing with 261. So 262, that's where I'm defining my input just like it is on the slide. So these two sine functions that I'm going to be adding together. Right, now I'm going to simulate running it through my filter, or the transfer function of my filter, in 264. So this is new. We haven't seen this before. I'm using this lsim command. It's actually pretty similar to using step or impulse that we've seen before. I'm giving it the transfer function, rf1, but this lets me put in any input that I want. It doesn't have to be a step or an impulse like those other ones. I can give it any arbitrary input function, and I'm giving it u as my input because that's what I just created. And I do also have to tell it the timestamps for that u. So u and t are correlated in that way. So that's what lsim is doing. So the transfer function, the input, and the timestamps, and what it's going to give me out is this y, and that's the output at those same timestamps. So that's going to be the output voltage when it passes through my filter. So then what I can do is I can plot what's my original signal look like, u, that's going into the filter, and then what's the filtered signal or conditioned signal going to look like, and that's y. And I'll put them both on the same plot, and we'll see what happens. So this is what we get coming out. All right, so we see here in blue, I'm illustrating what that unfiltered original signal was. So that's the one that's given here, the 5 sine 0.5t plus 0.6 sine 100t. So that's in blue here. Now the red is the output. Once it goes through our filter, what does it look like then? So in red, we see the filtered signal. Right, so one thing is apparent, the high frequency part of that's this rapidly changing value, that's the 100 radian per second part of the signal. That part of it is much smaller. It should be about 30% as large in amplitude as what we saw before. However, the slow moving part of the signal, that 0.5 radians per second, that's been pretty much preserved here. We see that the slow moving part of the red line matches that of the blue, whereas the high frequency is much different. It's much smaller in the filtered signal. So we have low pass filtered our signal, and we can see the results here. So through the simulation, it looks like our filter is successful based on the transfer function we came up with. But how do we actually make this 5 Hertz low pass filter? We know what its transfer function should be, but how in hardware, if we were building an analog device, would we do this? So again, this was the desired transfer function we wanted our filter to have for this first order low pass filter. And we decided a 5 Hertz cutoff, so we are setting that omega c to 10 pi. So we can make a circuit that has this transfer function, and we've seen this before when we were looking at first order systems. So in this case, if I put a resistor in series with a capacitor and then have my output voltage be the output across the capacitor, well, that is going to have this form of a transfer function like we saw before. So it's going to have the form of 1 over RCS plus 1. So what are we looking for here? We have we want the coefficient in front of S to be 1 over 10 pi, and RC is going to be the coefficient in front of S. So if we pick R and C such that when we multiply them together, it's 1 over 10 pi, well then we've made a first order low pass filter specifically with a cutoff of 5 Hertz. So any combination of resistance and capacitance whose product is 1 over 10 pi is going to successfully make this low pass filter that we're trying to create. Now, there's a whole range of resistors that we could choose. There's a whole range of capacitors that we could choose. If we were actually going to build this, we would probably target some capacitor that we wanted to use, since they're going to be fairly small values in the millifarad or microfarad range. That's going to be more of a limiting hardware design choice that we're going to have. So we could select some C. Then, based on the C that we're going to be working with, we have a lot more selection in the resistors, or maybe put a couple of resistors together to get an equivalent resistance, so that when we multiply the equivalent resistance times the capacitance, we're getting that 1 over 10 pi, or at least as close as we can get. In reality, we're probably not going to be able to get exactly 1 over 10 pi to be their product, but we want to get pretty close.